I want to welcome you all to the Faculty Academic Staff Forum at UW-Eau Claire, and I'm adding UW-Eau Claire because we have our online viewers who may be tuning in from elsewhere. I'm delighted to see such a big crowd for today's speaker, so welcome all, and I'm delighted to introduce our speaker today, Dr. Elizabeth Radue. She's an assistant professor in the Physics and Astronomy department here at UW-Eau Claire. And the title of her talk, which you can see behind me as well, is Harnessing the Power of Light, Absorbing and Emitting Light with Organic LEDs. Before I turn things over to Dr. Radue, I have just a couple of announcements. So of course, after the presentation, we'll have about 10 minutes for questions. And for our remote viewers, if you have a question, please submit them using the Q&A function at the bottom of your screen, and our wonderful graduate assistant, Matt, will read those questions aloud to Dr. Radue. When we do have questions from the audience, Dr. Radue, I'm going to ask you to briefly restate the question just for the benefit of our online audience. And then the last note that I have is that there will be a fire alarm today at 12:45. So, Dr. Radue has kindly abbreviated her talk to accommodate that and to still allow time for questions. But when the fire alarm happens, I'll just ask you to exit to your left and then right out the main doors of McIntyre Library. Without further ado, please join me in welcoming Dr. Radue.
All right. Thank you very much for that kind introduction. Yeah, there's nothing like a fire alarm to give you a hard deadline for a talk. So I had a mentor in grad school who always urged me to start with acknowledgements with the people I've worked with, because it's important to not forget the people who helped you get where you are. So because this work builds on a lot of the work that I've done previously, including work that I've done at the College of William and Mary, where I did my graduate work, the University of Virginia, where I did my postdoc work, including other collaborators, and as well as my current collaborator, Dr. Rubicki, and of course the ORSP for helping provide funding to do this work here. All right, so that being said, let's start out with why organic light emitting diodes are so fantastic. Why do we care about them at all? And just a little aside, I did try to make this talk for a general audience, which I believe allows me at least one scary physics equation in the entire talk. Okay. So, but no, we won't start with that. All right, so organic LEDs. So yes, OLEDs, these are the same OLEDs in your super fancy displays that have the blacker than black. And the reason why they can have such dark black is because instead of with LCDs, where you have lots of layers and you just kind of have white light behind, which then you have to filter out to get the various colors to come through. Each individual pixel has its own little individual light that you can turn on and off. So when it's off, it's really off. It's not just blocked. The other thing with organic LEDs, those organic layers, those molecules are very flexible, and you can create bendy screens and actually provide the ability to create those phones that you can fold in half without breaking your screen and collapsing into lots of pieces. Other advantages, it gives us a broader range of colors. It doesn't emit quite as much ultraviolet light, which we don't want more ultraviolet light if we can help it. And it's a little bit more energy efficient than some of our traditional LEDs, light emitting diodes. So I came to this project by collaborating with Dr. Rubicki. He had been building these devices and looking at them for a while. And to build an actual OLED device, you have to stack a few layers on top of each other. Now, our magic layer here is this organic, which I'm labeling here as ALQ3. It has a much longer name, but I can never remember it. That is the layer that actually produces the light. And so on top of it, we have a calcium layer, which helps inject electrons into our ALQ3 layer. And then we've got our ITO layer, which is greedy for electrons and will steal them away. And you can see the electrons that pop in from calcium have a lot more energy. That's what this little block means. The electrons up here have more energy. And to get from the calcium to the ITO, indium tin oxide, it has to make a big jump. And when it makes that big jump down, it emits light, and hence that's where our light comes from. So this is a nice little side schematic, but this is way blown up. These layers are actually on the orders of nanometers thick. And if you were to look at a device, you would see something much more like this here. And there's actually 3 different devices here. And this was built by one of Dr. Rubicki's students, Luke, who is passed on, and passed on meaning he graduated. As soon as our students leave, they're dead to us. All right. So where do I come in? So Dr. Rubicki noticed a long time ago that how you grow these devices, how you build these devices, change very much how they behave. So the 2 basic methods that he used was thermal evaporation, where he had a little, tiny little pot that he had under a heater. And by heating it up, he essentially evaporated it, and the evaporation sprayed up and was able to deposit a very thin layer on the substrate that we're growing the device on. The other way that you could grow these devices is, instead of using heat, is you send a large stream of electrons and bombard the surface with the electrons, which then, similar process, kicks off atoms, which you then can deposit on a surface. But the devices built with electron beam evaporation were not quite as efficient as the ones built with a thermal evaporation. But in addition, it started to have a strong magnetoresistance behavior, aka when you expose it to a magnetic field, you change the resistance of it significantly. So when I say resistance, I mean how easily it lets electrons flow. So it doesn't take quite as many batteries, quite as much power to make the electrons flow through the device. Will produce X-rays. It's called the Bremsstrahlung effect. So these organic films, this ALQ3, was being exposed to X-rays. And Dr. Rubicki identified that as the main difference between these 2 devices. So here is a nice little video. So yeah, why do we care about making crappier devices? As shown here in this nice little video, you can actually do some pretty cool stuff if you bring a magnet close to it. So we've got our device looking super refined and pretty, and we bring a magnetic pen close to it, and all of a sudden, all right, we see a graph. We're seeing a lot larger flow and current. That's what those lines mean. Closer, more flow, farther away, less flow. And this is a possible way that we could interact by using a magnetic stylus. So it's turning on by bringing it close, turning off by bringing it far away. And you could extend this to an entire touch screen. So yes, they are less efficient, but it is pretty cool what we can do with this, with that kind of control with magnets. But this organic magnetoresistance effect is, they still didn't have a good understanding of why there was a difference between X-rays and no X-rays. What is the underlying mechanism? What's going on under the hood in this organic layer that's causing this to happen? And I suspect there's something structural about this. Dr. Rubicki talked to me about it, and I had some ideas about how we could get at it. However, my go-to measurement technique for measuring structure within a molecule is to use X-rays, which is a no-go, because that means the way that we're measuring it is inherently changing what we're measuring, which is not good scientific practice. So the method that Dr. Rubicki used frequently was X-ray photoelectron spectroscopy. Kind of gives you information about where the electrons are in it. I like to use X-ray diffraction. I'll talk more about later about how you use that, but just the main takeaway is that it's a lot of X-rays. It's no-go. So my solution, let's look with lots of different colors. So X-rays is part of our electromagnetic spectrum, but it's not the only part of our electromagnetic spectrum, and that includes visible light. So I'll talk about in this talk 3 different ways that we can safely probe these samples without changing them and hopefully get an idea of what's going on exactly. So, and I will preface this is not an exhaustive list. I'm sure there's many more techniques that I'm not covering today. Don't at me, but yeah, please come talk to me afterwards if you want to talk more detail why I'm looking at these ones. All right, so let's go back. What is light anyway? So as I said, is an electromagnetic wave, which unless you're a physicist already is probably gibberish to you. But essentially a wave is very much like an ocean wave. So in the water, you've got waves in the water, and at the surface, you've got motion going up and down, and it happens in a very regular pattern, a very periodic pattern. And if you were to set, I don't know, say like a little ducky on the surface of the water, as the waves pass by, you would see that ducky go up and down in response to the waves. So electromagnetic fields are made up of, or electromagnetic waves are made of electromagnetic fields, which requires at least 3 years of physics to explain, but essentially it's the same idea as these water waves. You place an electron in an electromagnetic field, and it's going to have that same bobbing motion. It's going to feel that force up and down, up and down, up and down. And essentially light is kind of meaningless unless there are charged particles that can respond to the field. So something that has either a positive charge like an electron or like a nucleus, or a negative charge like an electron. All right, so we got a wave, we got a regular pattern, but the gamut that these waves can go is astronomically big and terribly, terribly small. So here I've got a picture of all of the electromagnetic radiation that's out there, and we see we've got our visible light in the middle here. That's the light we see around us. It's the light we respond to with our eyes. And yes, there are electrons or molecules in our eyes actually responding to those electromagnetic waves. If we go on the shorter side, we've got those ultraviolet rays. Those are the ones that give you burns, which is why we don't want UV light. Even shorter, we got X-rays, and we can penetrate inside the body and objects, although it's even more damaging than ultraviolet light, so we have to be even more careful. And on the way dangerous side, we've got gamma rays, which come from basically nuclear reactions, and are light and are incredibly damaging. But on the positive side, they are used to kill cancer cells very effectively. And then over on the longer range, we've got infrared light. So if you ever use a night vision goggles, that's what that's picking up. That's every heated object emits infrared light. So you glow in the dark if you can see in the infrared. We got our microwaves. Yes, the same microwaves that's probably cooking your burrito right now if you're watching from home. And all over here, we got radio waves, which is all the wavelengths and the meters long. And yes, are the radio waves that send your radio signal when you tune in your car. So, all right, so we got our tool set. Now, what are we looking at anyway? So I want to investigate this material on the molecular level. And there's kind of two avenues for that. The first one is how far are these atoms from each other? What is the structure? How are they related to each other? So here's a diagram of our AlQ3 with the full name tris 8-hydroxyquinol aluminum. Dr. Rubicki can correct me on that later. The other thing that we can look at is how free are the electrons to move around. So if the electrons are tightly bound to their atoms, they're not going to be able to strongly respond to any waves that are coming through. But if you got a lot of electrons in your material that are free to jump around a bit, then we're cooking. And we'll kind of talk about more on how exactly they will respond to light. This method that won't work because we're exposing X-rays is XRD. And the reason why I love this for measuring structure is because X-rays make a fantastic measuring stick. So the wavelength is about 1.54 times 10 to the negative 10th meters, about 2/3 of the size of a water molecule, insanely small. But that is the perfect size to measure spacings between molecules. And we send our X-rays on a setup like this. We bounce it off the material into a detector, and we'll get some kind of regular pattern that looks like this with periodic peaks. So what do those peaks mean? Well, they correspond to points where there are equally spaced layers within your material. So light has an awesome property that if you send two beams down different paths, if the difference between those paths is the same as a whole wavelength, they're going to constructively interfere. They are going to boost each other up and become more powerful and create those bright peaks. If, however, they are exactly a half a wavelength apart, they're actually going to cancel each other out and you will get nothing. So as we bounce our X-rays off of our different layers within our material, and this is true of any regular spacing, not only just nice straight layers like this, as long as the difference between the light that bounces off the surface and the light that bounces off the next layer follows this rule, you're going to get a really bright peak. And then you can use this fancy equation here to back out what is that distance and get the structure. As I said, it would be a great tool if we could use it, but I don't trust it because it would be inherently changing our samples. So let's move on to our next tool. And that is Fourier transformed infrared spectroscopy, which is kind of a mouthful. And this is measuring vibrations within a material. So we are now way into the infrared. And the thing about light is the longer wavelength you go, the less energetic the light is, and AKA the less destructive it is. So we are very safe as far as being far away from destroying our materials. The wavelength is on the order of microns, that 2.5 times 10 to the negative 6 meters to 25 times 10 to the negative 6 meters. So we're on the range of like a human hair as far as size. So we're it's going to unimaginably small to somewhat imaginably small. All right, so we're looking at vibrations in the material. Why would I care about vibrations in the material? So anytime you have atomic bonds, I'm going to try not to lose my little ball here. The forces between them is very much like a spring. So if we imagine this weight in my hand, they're going to pull back on each other. If there's any distortion from the main position, it's going to pull back. And as it goes back and forth, it's going to go back and forth with a very regular frequency. And if that back and forth happens to slosh around some electrons, that means it's able to absorb infrared light. And so there's various ways we can have wiggles. I have some examples up here, symmetric stretch, antisymmetric, and I'm not going to go into great detail. But that is to say, if you have some difference in concentration of electrons in different parts of your material and they move relative to each other, they can absorb light. And the light that they absorb is going to be very specific to what frequency they wiggle at. And so from that, we can kind of get some information about the structure because the amount that it wiggles is very dependent on the structure. So this is the case. This is a new project for me, so I don't have a lot of data, but this is our fresh off the press, ugly graph of data. And what we have here is an FTIR result. And we can see these spikes of strong absorption. That is where we had very strong absorption of infrared light. So I sent out, or my student specifically, Annika Ricks, who did a beautiful job here, sent out a large range of light. Don't worry about the units here, but it's various wavelengths of light. And we see a nice fingerprint that matches with ALQ3, where we see absorption. And the red curve is unexposed ALQ3. It has been untouched. It is fresh off the press. And our black curve that is hiding with the smaller peaks is UV exposed ALQ3. So the UV is energetic enough to hurt it the same way that the X-rays are. And we found that we saw, yes, a substantial change in our phonon modes that we can detect with FTIR. So what can we say about this? Well, we're still working on interpreting this. But I will say we haven't seen any of these peaks shift. So that tells me that the frequencies of any of these variations are not changing. So that's not going on. And we see an overall decrease in amplitude across most of these bonds here. And that suggests to me that we have bonds breaking just kind of across the board. So it kind of backs up that, yes, there is a physical change going on. All right, so let me talk to my next tool then, Raman Spectroscopy. And this is sort of the sister measurement for FTIR. It is also measuring those vibrational modes, but we can measure them with visible light, so red or green laser. And it's not straight up absorption. It's basically very rarely when you send light at a material, Most of the light that scatters back will be the same wavelength that you sent in, but occasionally you'll have something called an inelastic collision. So that should be familiar to my physics students in the room. But basically an inelastic collision, if you throw a ball at something and it loses a little bit of energy on the bounce, and when it hits something, then it's going to come back with less energy. So sometimes the light hits the material and it loses a little bit of energy, and that energy goes to the phonons. And sometimes it gains a little bit of energy from the phonons. So you'll see a little shift in the light, either to red or blue. And by looking at those shifts, how much it's shifted by, how powerfully it's shifted, again, we can see, okay, we got phonon mode there, we got wiggles there, we got wiggles there. All right, and so we haven't done any measurements yet with ALQ3, but part of why I wanted to bring it up is because I did use this previously for my graduate work to look at a material called vanadium dioxide. Now, vanadium dioxide is a material that goes through a phase transition. Basically, when you heat it up, it goes from something that's a really crappy conductor, it doesn't let electrons pass through easily, to a great conductor, much more metallic. And what's awesome about it, it's reversible. You can go back and forth, back and forth, back and forth as many times as you like. And we were trying to figure out, is this mostly an electronic phenomenon or is it a structural phenomenon? Because both are going on, but which is the chicken and which is the egg? And so for this experiment here, we heated up our sample. And so blue is colder, red is hotter. And as we heated it up, we saw some of those peaks disappear. And those peaks corresponded to these pairs of atoms right here. So this is the low temperature state right here versus the high temperature. And in order to make that transition, those bonds had to break, and that energy would shift quite significantly. So this is part of why I'm interested in, okay, I think there's something structural going on in this organic material. I think this is a good tool to look under the hood. All right. And the last tool I have, in the little bit of amount of time I have, is a technique called surface plasmon resonance. So this is more looking at the electrons. How mobile are they? How much can they move around? And there's a phenomena where if you think about your free electrons as kind of a sea of electrons that can slosh around, they can make waves. If you couple in your light just right, the light and the electrons are kind of synchronized and start traveling with the same frequency and same speed. And you get really strong absorption. So like in metallic, like gold, where you'd ordinarily expect there to be very strong reflectance, light should be totally bouncing back at you, you actually see a really dark spot. All right, here's my page with the very scary equations. So you don't have to understand. What I want you to take from this page, though, is that the conditions for this resonance are very, very, very sensitive to the optical qualities, which is very, very sensitive to the free electrons in all of these materials. So if any of these shift, where my absorption happens is going to shift as well. So it's a very sensitive tool for measuring changes. So again, I haven't set this up, but previously working with SPR, or surface plasmon resonance, I was able to detect electrons being injected into a material. So here is a picture, and the red is it's highly reflective, and the blue streak in the middle here is where it's highly absorbing. It's almost completely absorbing. And we were able to shift that line by using a very powerful laser to inject electrons in the material. And we were actually able to very closely predict, based on how many electrons are injecting, how much it should shift. All right, and the other reason why I want to kind of get into this is because there is another application for this organic layer, and that is to create solar cells. So our organic LED, we provide electricity to it. It flows electrons across, it produces light. But you can reverse that process. So you shine light in, it causes our electrons to jump our layers, and then it causes them to flow and produce electricity whatsoever. And the nice thing about this is that we can have flexible solar cells, again, because that organic layer, it's very flexible, unlike our glassy traditional materials for solar cells. And surface plasmon resonances, you can create conditions where you have very high absorption into your solar cells and have better efficiency, which is always good. All right, so I talked a lot at you today, but I hope the main takeaway that you take is that light is cool and you should study it, and everyone should have a laser beam. All right, so I will open the floor for questions. Thank you.
When
Yes.
you were damaging the film with UV to try
Yes.
to simulate the damage from X-rays?
Yes.
What level of UV did you? I mean, is it?
So we used a home UV lamp. Oh, sorry. Thank you for reminding me. So the question was, when I was exposing these samples to ultraviolet, what was the level of exposure? How intense was the exposure to these samples? So we're a little bit in the testing ground right now. So we don't have a number, but we use basically a home handheld UV lamp and just held it over it for a period of time. So we did an exposure of like 5 minutes to 10 minutes up to an hour, and we saw a pretty significant change after an hour. But if you wanted hard numbers, no, we're going to have to be a little more diligent on measuring that in the future. Any other questions? Yes.
So by using all three techniques,
Mm-hmm.
which each tell you something a little bit different,
Mm-hmm.
about that, you would be able to describe.
Yeah, yeah. So my hope is, and it's a promising start so far, is that the FTIR and the Raman Spectroscopy can tell us about the phonon modes and the structure, and are there bonds breaking? Are there bonds shifting in energy? And then the surface plasmon resonance can help us tell us about what we call the electronic structure, or how free the electrons are to move. So maybe it is that there's both structural change and it's causing more electrons to go to a higher energy state, possibly, or a lower energy state. And yes, Raman and FTIR seem like they're measuring the same thing, but there are actually vibrational modes that are sensitive to infrared absorption, and there are ones that are just sensitive to Raman spectroscopy. So we can kind of take a peek at different vibrational modes with the two different methods. So that's why I want to incorporate both.
So with the FTIR and the Raman, I don't know that much about them. Are you reflecting things off the surface, or are you passing it through the body of the material? And if you're just reflecting it off the surface, are you confident that you're still getting information about the bulk of the material?
Great question. So the question is, what is the geometry for these FTIR and Raman measurements? Am I reflecting off the surface, or am I passing through? And the reason why it's a great question is because we're dealing with very thin films that they don't exist by themselves. They're deposited on a bigger glass substrate. So you can't just have one. And if I were to pass the signal through, there are ways that you just pass the signal through. I'd be picking up signal from my sample, but I'd also be picking up signal from my glass substrate. So I am reflecting off the surface for both, and I'm still picking up a little bit of the glass. However, Annika specifically is accounting for that, and she's measuring the glass sample by itself and then subtracting it from the data. So we're just dealing with a baseline. And then to answer your question, how confident I am that I'm measuring what I want to measure, I go to previous research who has measured this before, and do my peaks at least roughly match up with what's been done before? And yeah, we're dang spot on. So we're confident that we're looking at the right thing. Yes.
Okay, so I recently bought a new TV. Right?
Okay.
Choices for like QLEDs and OLEDs,
Uh-huh.
LCDs. So I ended up buying a QLED TV instead of OLED because the like whites were whiter, like it was brighter overall. But like, is there an opportunity to incorporate like quantum dots or other materials with this layer, or like you just is one layer?
All right. So the question is about purchasing TVs, and Liz over here has recently purchased a QLED, or a quantum LED, which uses slightly different technology. And thank you for showing my growth edge, because I do not know the answer to that question, because I do not know a lot about QLEDs and how we can incorporate the two together to have the whiter than white and blacker than black. All right, any other questions? Put me on the spot. All right, so now that we've established, yes, we are seeing a definite change with this exposure, and we have kind of idea of how high an energy photon we need to actually create the change. It's now back to Dr. Radue to build the devices, because I just looked at the ALQ3 by itself. I didn't look at actual devices. So his students are now building devices, and now we're going to have, all right, we're going to expose them. My student's going to measure FTIR, but then we're also going to look at the light coming out, and so kind of correlate that performance, that magneto resistance with the FTIR and see how they link together in a more scientific way.
So you talked a little bit about flexibility of
Mhm.
screens and solar plant panels.
Mhm.
Are there other applications for this type of research that you can share?
I mean, so as I mentioned in the beginning, it does give us a wider array of colors that we can have, and having more energy efficient screens and light sources is always a good thing. Beyond that, I glossed over another aspect of Dr. Radwe's research, which was to create something called spin valves. Essentially, create a magnetic valve. So if you have a magnetic field on, you're going to allow current to flow. If it's off, it has to turn off. And of course, as part of all physics research, there's sort of the fundamental question of like, what physics principle is underneath this? And understanding exactly, all right, this is what's happening, it's because of this reason, it'll help us identify different materials that could be potentially used and might have other properties that we like even more. Yes, so sorry, to recap the question is, what are the other applications besides having the flexible screens and flexible solar cells? All right, great question. Yeah.
This one is not about TVs, I promise.
Okay.
So building on the fact that these are flexible,
Mhm.
do you see any difference in the properties when you're flexing the material?
You know, we haven't explored that yet because we've grown them on glass slides and the glass slides themselves are not flexible, but that would be a really cool avenue for research because I could imagine areas of flexing, of compression and strain could absolutely affect qualities. And yeah, Dr. Radue, we should talk about this later. Yeah. Yes.
So if you're thinking about using these for solar panels, are you worried about the ultraviolet damaging them as you use them as solar panels?
So the question is, if I use them for solar panels, am I worried about ultraviolet damaging them? And the answer is yes. Well, no, yes, with a caveat. So one thing we need to rule out is this organic layer is very sensitive to oxidation. So if it's exposed to air and light, it undergoes damage. Now we've established that the damage it undergoes is different than the one by UV. The one by UV and X-rays is definitely more acute. But one of our answered question is, does it need oxygen as well as the X-ray exposure to undergo this change? And if without oxygen it's safe, then yeah, it's probably not going to be a problem because it's going to be sandwiched between layers and it won't touch the physical air. Now, if it does still get damaged even without the oxygen, yeah, we'd probably have to worry about having some kind of UV filter on top of it to keep it long-lived. But we would also be missing out on a significant portion of the sun's spectrum. All right, one more question before the fire alarm. Is that a question or a stretch? All right.
I'm going to clap.
All right, thank you very much.